All right, thanks for tuning in, guys. We have a paper 2 for technical mathematics for the examination block of May June that was written back in 2024. The question paper has a grand total of 150 marks. Oh, for a moment I thought it was 50 marks, but it's 150 marks. And we have a time allocation of 3 hours. Due to the discussion that will be taking place in answering these questions, or the discussion centered around these questions on this question paper, the recording might go beyond 3 hours. But for you, you will be writing the exam. Of course, you'll have to finish you'll have to finish the exam within 3 hours. Now, then we have the instructions and information part of the question paper. This is important. Read your instructions, guys. Read your instructions. Read your instructions. They are very important as well. Né? So the question paper, based off instruction point number 1, we have how many questions in this question paper? 11 questions. Now let's check each question paper. So we have question 1. Question 1, it's analytical geometry. Question 2, it's another analytical geometry question. Question 3, question 4, trigonometry. Question 5, another trig question. Question 6, it's also trigonometry. Question 7, Euclid. Question 8, another Euclid question. Euclid. Question 9, still on Euclid. And then question 9 continues, and then we have another question on revolutions. Continues, a bit of Euclid there. And we have a question on, what is this? The midpoint ordinal rule. We have shapes, measurement, and a formula sheet for this question paper. Okay, so going back to the first question on analytical geometry. Let's tackle this question. All right, so for question 1, let's just understand what is really happening on the sketch. It's a diagram PQR, which is a triangle with vertices P, Q, and R. Lucky for us, all the points on the vertices of this shape are given. And we have N as the midpoint. N as midpoint. Maybe let me use green to highlight this part. This is important. So a midpoint, it's basically a point along a line that bisects that given line. You have a point that is called the midpoint along a line. It divides the line into 2 equal parts. So N being a midpoint, it means that NR is equals to QN. Let me use maybe blue. No, I don't write with blue. Let's just highlight with blue. Oh, that's purple. So this is equals to that. That's what the midpoint does. It divides the line into 2 equal parts. So we have a midpoint. S is a point on the y-axis. Another point on the y-axis. That point S can also be considered the y-intercept of line PR. Alright, done on the analysis side of the question. Now let's start answering some of the questions. In fact, not some, but all of the questions. So we have question. I have a plan. How about we divide the page like this? I think it's gonna be helpful organizing the calculations as well as the work. All right, because I dedicated only 1 page for each question, so I'll try to squeeze in all the calculation under 1 page. So we have question 1 being analytical geometry. Now we're gonna answer the first question 1.1.1 1.1.1. What are they asking for? The gradient of MQ, the gradient of PQ. So gradient PQ is equals to YP minus YQ, everything divided by XP minus XQ. Or you can just say y2 minus y1, x2 minus y1, x1. That's also gonna work. Just know how to differentiate between point 1 and point 2. Differentiate between the two. So yp, it's negative 2. I substitute. Let me put that in brackets. Minus, and then a yq, that's negative 6. Everything divided by xp, negative 5, minus xq, negative 1. Negative 1 equals 2. So negative 2 plus 6 divided by negative 5 plus 1. So the answer should be a positive 4 over a negative 1 equals to a minus 1. So that's a gradient of negative 1. So what we were doing, we were actually calculating the gradient of the blue line, PQ, not RQ, PQ. So the gradient should be 1. Now, what you should keep in mind as well is that a line that is tilted like this, a line that is tilted like this will always have a positive gradient. A line that is tilted like this will give a negative gradient, right? Hence, the blue line is tilted like the second one, this one. So that is why we have a negative gradient. Next question, 1.1.2. They want the coordinates of n, which is the midpoint. Another thing, guys, also consult your formula sheet if you tend or if you forget your formulas. What were we calculating? We were calculating the gradient. There's a formula for a gradient. Now we are calculating what? For a midpoint. You can use the formulas as they are, but just know how to differentiate or learn to label your points 1 and 2. So this is the midpoint formula, going back right here. All right, so the midpoint formula is, since the midpoint is n, I'm not going to use m, I'm using n. So n, that is x, the midpoint n is between 2 points, r and q. So it's going to be xp plus xq divided by 2, yp plus yq divided by 2, close bracket, equals to n. What is xp? Whoa, hang on. It's not xp, okay, it's not p, it's not between p and q, but between r and q. I made a mistake there. So xr is 5 plus, what is xq? Minus 1 divided by 2, yr, that's 4, yq, that's negative 6, close bracket, divided by 2, equals to n. 5 plus negative 1, so 5 you add it to a negative 1, you should get a 4 divided by 2. A 4 plus negative 6, that should be a negative 2 divided by 2. N is equals to 4 over 2, that's 2. And then the other one, it's 4, it's 2. So negative 1, that should be the answer for this one. 4, that's 2 and 1. So those are the coordinates of the midpoint. Now we have 1.1.3. How many? Okay, 3 marks. Now I just want to spend a little bit of time explaining this concept of the equation of a line, like actually how to find the equation of a line. You are asked to, like in 1.1.3, we are asked to determine the equation of a line. Let me use green again. Determine the equation of the line. Whenever you want an equation of a straight line, you're gonna need a point that lies on that straight line, number one. Number two, you need a gradient of that line that you want to calculate the equation for. Now, we are told that to calculate the equation of a line that is parallel, keyword, parallel to PQ, and it passes through R. Let me demo that line. Let me show that line. Let's use red. Let's use red. So the line is a straight line like this. It's a straight line like this, and it passes through R. Another piece of information is that this red line is parallel to PQ. Okay, so like I said, you need two things to find an equation of a line. The first one is getting a point. Check, we do have a point that lies on that line, it's R. Number two, we need a gradient of that red line before we can find the equation. All right, getting the gradient is easy because this line is parallel to that line. We know that parallel lines have equal what? Gradients. So the gradient of parallel line multiplied, what am I doing? The gradient of the parallel line is equals to the gradient of PQ. They are both equals to -1. How do I know? The gradient of PQ, we calculated it to be a -1. A -1. So now parallel line is equals to gradient of -1. We also have a point, so we have two of the things I was talking about. So now we go straight to finding the equation. We're going to use y equals to mx plus c to work out the equation. All right, so we have R as the point, 5 and 4. Now I have m, which is the gradient. I need to calculate c. We're going to substitute the point R as well as the gradient into the equation so that we can work out c. Now y, it's 4, equals to gradient, it's -1, x, that's 5, plus c, 4. So the -1 times the 5, that's going to be a -5, so -5 plus c, and then 4, bring the 5 over to the left. We now have a 4 plus 5, and then when we add, we get a 9. Now the overall equation becomes, we just substitute the gradient, -1x, c, that's 9. This is the equation of the straight line, of the red straight line. This is the equation. Let me just highlight it like this. All right, now for the next question and the last one on question 1.2, show by analytical methods that PQ over Sn is equals to 2. We can just calculate the distance PQ and calculate the distance Sn and divide them and see if we do actually get the 2. So for 1.2, I need the not the gradient, but I need this 1.2 PQ and Sn. I need to find the distance PQ and Sn. Let's start by finding PQ. PQ is equals to the square root, using the distance formula to work out the lengths PQ, that is xp minus xq squared plus yp minus yq squared. Then we have PQ equals to the square root of xp, that's minus 5, minus xq, that's minus 1 squared, plus yp, that's negative 2, minus yq, it's minus 6, close bracket, squared. And then we have pq equals to, let's calculate, negative 5 minus negative 1, close bracket, squared, plus negative 2 minus negative 6 squared. I'm getting a 4 square root 2. 4 square root 2. Then we also work out Sn. Sn is the square root of xs minus xn squared, plus ys minus yn squared, equals to the square root xs. Okay, so we are looking for this distance. Okay, I see what they were doing with this question. So this is actually the midpoint theorem, but we're going to talk about that. Not now. xs, we have, okay, so we need the coordinates for n as well, but we did calculate them. Coordinates for n, that is 2 and minus 1. 2 and minus 1. Okay, so xs, it's 0, minus xn, that's 2 squared, plus ys, 1, minus yn, that's negative 1 squared, is equals to, then we calculate 0 minus 2 squared plus 1 minus negative 1 squared, and then I get a 2 square root 2. Now here's the analytical method to prove this. We now take PQ divided by SN. PQ is 4 square root 2, 2 square root 2. Cancel, 4 over 2, that's 2. This is the final answer, and we just proved that 2 is equals to the division of this. We can also go about it using gradients, but I'm not going to go over that one. The distance method works just fine as well. Okay, now let's jump to question 2. Alright, this question 2, it's another question on analytical geometry. So we have 2.1. Where's the marker? Okay, let's use this. Right, yeah, perfect. Now 2.1 and 2.2, where we have to sketch an ellipse. Okay, so it's a two-part question where we are dealing with a analytical geometry question, that's circle, and we have a what is this thing called? Ellipse. Okay, so again, let me just divide the paper like this. Okay, first let's get rid of this, and then we divide the paper like this, and then I drag it down again. Okay, now in the diagram below, O is the center, so we are told O is the center. We have a center O is the center of the circle at the origin. This is important. O is the center of the circle at the origin. ML is a tangent. Another piece of information that is important for answering this question. To the circle at this point M. L is a y-intercept of ML, D is a point on the x-axis, B is an angle of inclination. Another important part of the question. B, that's an angle of inclination. Alright, so this circle has what we call a radius. So let me just connect this point and the center like this. Okay, not on the point I want it to be. Alright, there we go. That's a radius. There's no way. Okay, there's nowhere where they say we need to show the radius, but it's gonna come in handy for a part of the discussion. Now, they want us to determine the equation of the circle for 2.1.1. For 2.1.1, they want us to find the equation of the circle. So since this is an equation, since this is a circle with the center at the origin, we're going to be using this equation. X squared y squared equals to r squared. Okay, so what we have to do is actually find r, the radius of the circle. So the only way to do that is actually finding a point that is found along the circle. In this case, M is a point that lies on the circle, so we're just going to take it and substitute it into the equation so that we can calculate r. In fact, we are looking for r squared, not r. Yes. Then we substitute minus 5 y, that's 12, squared is equals to r squared, like this. Then minus 25, that's 25, minus 5 squared, that's 25, plus 12 squared, that's 144. And then we add, we get 169. This is r squared. This is what we want, an r squared. We are looking for an r squared because I have to leave x as is, y as is, just substitute this value only. So therefore the equation is going to look like this: x squared plus y squared is equals to r squared, which is 169. That's our answer for 2.1.1. For 2.1.1, this is the answer for 2.1.1. Next question, 2.1.2. Determine the equation of the tangent ML in the form y equals 2. So we need an equation for a straight line. You still remember this question question 1, where we had to find an equation for a straight line. We are given another case where we have to find another equation of a straight line. This time around it's a tangent. Okay, it's a tangent. Again, the tangent is a straight line. To get an equation of a straight line, you need a point. We have one. Check. What's missing? It's a gradient. So in the context of a circle, since we don't have 2 points, that's going to allow us to calculate the gradient directly. So instead we'll have to find or use other means of calculating that gradient. So here's the reason as to why I showed the radius. In analytical geometry, in Euclidean geometry, one of the theorems states that a radius is perpendicular to what? A tangent. So we're going to use this property to find the gradient of the green line, the tangent. So we know that the gradient of the tangent, when multiplied by the gradient of the radius, it should give us a -1. So we're going to calculate the gradient of the radius. That's the easy part because I have 2 points that I can use to find the gradient of the radius. So we're going to say mr is equals to yo minus ym over xo minus xm equals to, what is yo? That's 0 minus ym, that's 12, divided by xo, that's 0 minus -5, like this, equals to, I'm getting a -12 over 5. So that's the gradient for the that is the gradient for the radius. Now let's go ahead and calculate the gradient of the tangent. So m tangent multiplied by mr should give us a -1. M tangent, it's what I want. M tangent multiplied by mr, that is a -12/5 equals to -1. So it's either I divide by the -12/5 on both sides, or I can just multiply by the multiplicative inverse on both sides. -5/12 multiplied by -5/12 as well. So this cancels that, the 12 cancels that. Or you can just do the dividing thing, it's okay. Gradient of tangent, it's +5/12. So therefore we're going to take this gradient and work out the equation of the tangent. So we're going to say y is equals to mx plus c. Gradient we substitute. For the y and the x, we're going to substitute the m point. Y, that's 12. Gradient, that's 5/12. And then x, it's -5 plus c. 12 is equals to, we multiply that, we get a -20/12. Okay, they're not equals to, but plus c, plus c. And then we transpose, we get a 12 plus 20/12 is equals to c. We add those two, we say 12 plus 20/12. 20/12. Alright, no, wait. I see I made a mistake. The 5 times 5, it's not 20, it's 25 instead. I see the blunder I made here. So it's 25. And then that's 12 plus 25/12. I'm getting a 169. 169/12 is equals to c. Therefore, the equation of the tangent looks like this. The gradient is 5/12 x, and then c, that's plus 169/12, like this. So that's the equation of the tangent. Where's my marker? Alright, let me just highlight it like this. Alright, next up is to calculate, or write down the coordinates of L. Now, they say write down, not calculate, write down. So, actually the C value of that straight line, look, they did mention that L is the y-intercept of line ML. So, the coordinates of L are actually the y-intercept of the straight line ML. So writing down the coordinates of 2.1.3, L is just going to be 0, and the C value of that straight line, ML, the one we just calculated before. So the value for C, it's 169/12. 169/12. So these are the coordinates for L. Determine the size of B, the angle of inclination. Okay. 2.1.4. We are looking for beta this time around. Okay, 2.1.4. We're going to be using this formula. The gradient is equals to tan of theta. In this case, we're going to be saying beta. The angle beta, it's the angle of inclination, represents the angle of inclination. The m, it's for gradient of the line that creates that angle of inclination. Okay, so the angle B is being created by line MD. Let me highlight. This purple line creates the angle of inclination B. So we should be looking for the gradient MD. Therefore, gradient MD is equals to ym minus yd. Then we divide the whole thing by xm minus xd equals to what is ym, that's 12, minus what is yd, that's 0, divided by what is xm, that's minus 5, minus what is xd, that's negative 3, equals to 12 over negative 5 plus 3, that's going to be negative 2, equals to a negative 6. So that's the gradient. Okay, my brain is half awake, so I need to verify the calculations. Minus 5 minus 3, just to check. Okay, negative 6. Negative 6 is the answer. So we have the gradient. Now it's time to calculate. Wait, hang on. Okay, like this, like that. Yeah, okay, it is negative 6. It is negative 6. But now, okay, alright. So therefore, we're going to say gradient 6 is equals to tan b. You see what I did? I did not include the negative sign on there. Therefore, beta is going to be 180 minus arctan of that gradient 6. And then we punch that in. 180 minus arctan of 6. I'm getting a 9946 if we round this off to 2 decimal places. In fact, we should, because that's what the instructions have stated above. So that's 99.46 degrees. That is beta. If you have a negative gradient, you want the angle of inclination. You don't include the negative on your calculations. Then when you calculate the angle of inclination, you're gonna subtract the value of the arctan from 180 degrees, right? Anyway, by just looking at the angle beta, the angle of inclination, it should be bigger than 90 degrees. So it makes sense. It makes sense to say 180 minus. Now for the last question, 2.2, we have to draw on the grid provided on the answer book the graph defined by, this is an ellipse. This is an ellipse graph, okay? An ellipse graph. I don't know how you guys plot this thing in class. Let me just grab the grid. Let me grab the grid. I have the answer book. I have the answer booklet. Okay, yeah, maybe next time I record these videos, if the folder has a answer book, I'll just try to squeeze that in. Alright, so this is the grid they are talking about. Okay, maybe this was a bad idea. Let me try putting it here. Yeah, let me try putting it here. I'm gonna hide this part. Yeah, because I don't know what's happening. I don't want the grid to be below the writing. I want it to sit on top. So on the writing paper, I see that I have a bit of a problem. Okay, now I'm just gonna label or mark down the grid like this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. -1, -2, -3, -4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, then a negative 8. So how do you plot an ellipse? I don't know how you guys you were taught in class, but the best way to plot an ellipse is to take the square roots. Let's use purple. To take a square root of this value and take the square root of this value as well. So the square root of a 3 squared, square root of 3 squared, that is equals to a plus minus 3, and the square root of a 36 is equals to a plus minus 6. That's the easy way. That is the easy way out of this one, right? But plotting an ellipse is just you need an x-intercept. So you need an x-intercept and a y-intercept. So for the x-intercept, you let y to be 0, you solve. Then for the y-intercept, you let x to be 0, you solve, so on and so forth, right? But at the end, you're gonna end up with this as your y-intercept. This is the y-intercept. Why the y-intercept? Because the 36 is the denominator of y, and then the plus minus 3, that is going to be the x-intercept. What am I saying? Yeah, the x-intercept. The x-intercept, that's going to be a plus minus 3. Why? Because the 3 squared was the denominator of the x variable. Alright, then we plot the plus minus 3. This is negative 3. This is plus 3. And then we have the orange. The orange that represents the y-intercept. This is the y-intercept. So that's 6, positive 6. And negative 6 right here. And then we connect everything. We connect everything. We connect everything. You don't connect by lines. You connect using curves like this. Not as perfect, but yeah, it sends a good message. Now that's 2.2 for the question 2. That concludes the question 2, and now we're gonna jump to question 3, which is a trigonometry question. Alright, again we divide. Okay, perfect. We divide, but I'll have to erase the work that I'm gonna do for question 3 to make space for question 4 as well. Like I said, I dedicated a single page, a single writing pad page for a single question. Now I have question 3 and question 4 on the same, dedicated to the same page. So question 3, trigonometry. You know, I'm actually teaching pure maths and a little bit of technical mathematics. In pure mathematics, this trigonometry. Okay, maybe let me say question 4 is more of the pure maths kind of trigonometry type of asking question. Maybe question 5 as well, but in pure maths we also don't have the inverse functions, right? So that's a little bit extra that you have, you guys. And then question 3, okay, question 3, now you won't find something like this. So what I'm trying to say with question 3 is that this is easy grab marks, easy marks to grab, right? You do substitutions for 3.1, then you punch that on the calculator, you round it off to 2 decimal places as stated on the instructions, unless maybe they asked you to round it off to 3 decimal places, but you just punch in the calculator, you round it off. Like for the 3.1, 3 point or 3.3.1, 3.1.1. Okay, so therefore we got a cosec p multiplied by a tan q equals to, now remember, we don't have a button that is dedicated for inverse function, so I cannot punch cosec on the calculator. I'll have to use its inverse. In this case, the inverse for cosec is what? It's sine. Then we substitute p, that's 119, multiplied by tan q, that is 61 degrees. Then you consult your calculator. 1 over sine 119 multiplied by tan 61 degrees. Then I get a 2.06. That's 2 decimal places. And then we're gonna do the 3.1.2. So for that one we get a cos squared p plus 2q. So therefore we're gonna have a equal sign, a cos squared, and then p, it's 1 okay, wait, okay, 119. I thought it was 116. Then 2 multiplied by 61 degrees equals 2. Alright, on paper that's how you're gonna write it, but on the calculator this is how you're gonna do it. You first start by opening up a bracket, then you put in cos, and then another bracket. After pressing cos, it's gonna be cos, open a bracket, then you punch in that 119 plus 2 times 61. You close the bracket inside, then you close the bracket that you opened initially, that was the bracket for the cos function. Then you square everything. I'm getting a 0.24. You should be getting a 0.24. Rounded off to 2 decimal places. Okay, like I said, on paper this is how you write it, but on the calculator you cannot punch in a cos squared then open a bracket like this. No, it doesn't work like that. You start off by opening a bracket on your calculator, and then you say cos. After pressing cos, automatically a bracket will open up, and then you're gonna say 119 plus 2 times 61, close bracket. Then you close that bracket you initially opened, then you square, then you're gonna get that answer. Right, you're gonna get that answer. So this and this, it's one and the same thing, but on the calculator this is how you punch it. All right, then we get 3.2 given where the theta, this angle, it's between 0 and 90 degrees. All right, show without the use of a calculator that sine squared theta plus cos squared theta is equals to 1. That's a Pythagorean identity, or the square identity for sine and cos. All right, that is true, but we have to show it. Now we can use a diagram for this. Let me show you what I mean by this. We have a 1 over 2 tan theta equals to 2. I divide by a half, or I can just simply multiply by the multiplicative inverse like this, so that the 2 cancels out the 2, the 1 and the 1 out. Then we're gonna be left with a tan theta equals to 4. Equals to 4. Therefore, through a diagram, this is what we do. Using a diagram, we can do this. Using a diagram, so since this tan is between, since the tan is equals to is between 0 degrees and 90 degrees. It means that the triangle with angle theta should exist in the first quadrant. Should exist in the first quadrant like this. Like this. And then we're gonna have a 90-degree angle. Then we're gonna have theta. And then that 4, let's divide it by 1. Why are we dividing it by 1? So that we can have a fraction, since tan is a ratio. So based on that triangle, we know that tan, according to SOHCAHTOA, it's what? It's opposite, which is y, it's this, over adjacent, which is x. So x is equals to 1. The 1 is coming from there, and then y is equals to 4. The 4 is coming from there. That is why I had to divide by 1, so that I can have a ratio where the y will be assigned a value as well as the x can be assigned a value. What's missing now is the r value, the hypotenuse. We use Pythagoras theorem to work it out. So we're gonna say r squared is equals to x squared plus y squared equals to x, that's 1, y, that's 4, equals to r squared. So that's 1, is it 16? Yeah, that's 16. So 16 plus 1, that's 17. And then we're gonna have a square root of 17. So r is just gonna be the square root of 17 like this. So we have r as equals to square root 17. Now then it's time to calculate what? Sine squared theta plus cos squared theta. It's time to calculate this. So I'm just gonna say equals to sine, based on from SOHCAHTOA and that triangle. Sine, it's opposite over hypotenuse, so it's gonna be y over r squared plus cos, it's gonna be x over r squared like this, equals to, what is the y value? It's 4. R, it's square root 17 squared plus x, that is 1 over r is equals to square root 17 as well, squared like this. Then we continue. 4 squared, that's 16, and then square root 17 squared, that's 17, plus 1 squared, that's 1, square root 17 squared, that's 17, equals to, the denominators are the same, it's not 77 but 17. The denominators are the same, we're just gonna add the numerators and take the common denominator. 16 plus 1, that's 17. 17 over 17, that is 1. We just proved that a sine squared plus a cos squared is equals to 1. Now it's time for solving for x. Solving x. 3.3 sine x is equals to tan 318 degrees. Then we have a sine x that is equals to minus, no, it's negative because 318, it's in the fourth quadrant. So we have sine 318, bingo, that's 0, 9004 404 00 no, it's 0443, just 0443 443. There we go, 443. And then you now have a trigonometric ratio equal to some value. Then you can only calculate your reference angle this time. Okay, so therefore you're gonna say arc sine of this whole thing without the negative sign, of course. So it's gonna be 0.9004, so on and so forth. You just take the whole thing, shift sine of 0.9004 040443, close bracket. Then you end up with a 62.21 in two decimal places, 64.21 degrees. That's your reference angle. Now we're gonna have solutions. We're gonna have solutions in two parts of the cast diagram, right? So cast says in the fourth quadrant cos is positive, in the first all of them are positive, in the second sine is only positive, in the third only tan is positive. So we are looking for the part of the graph. I mean, our solution is going to be found in two distinct places. We are looking for parts of the Cartesian plane or the cast diagram where sine is negative. It's where it's in the third quad and the fourth quad. So that means that's where our solutions are going to be. In the second quad, I have this reduction formula, 180 minus and 180 plus theta in the third, and here I have 360 minus theta. Therefore, where sine is negative, it's the third and the fourth quadrant. So in the third quadrant, this is going to be my solution. It's gonna be x equals to, in the third quad, that is 180 plus the reference angle, which is 64.21 degrees, equals to 180 plus 64.21. I'm getting a 244.21 degrees. And then in the fourth quad, I have x that is equals to 360 minus 64.21 degrees equals to 360 minus 64.21. Then we have a 295.79. There we go. 79. So these are the solutions for that equation. So that concludes question 3. Now we're going to jump to question 4, which is a bit more, should I say aggressive? Nah, I shouldn't. Okay, let me just erase and we'll do question 4. Okay, now let's divide. Is that an eraser? Okay, there we go. Okay. Therefore, let me just drag it down a little bit like this. Okay, so now question 4, we are given an expression, a trigonometric expression. So for 4.1.1, simplify by reduction tan pi plus a. Now pi plus a, now remember, this is an angle in radians, right? In radians, so it's equivalent to 180 degrees. So this 180 or pi plus a is found in the third quadrant. Let me have a cast diagram prepared on the side like this, and include the formulas for each quadrant as well. So we have cast in the fourth quadrant. Let's start there. We have 360 minus pi. Okay, not pi, theta. So this is like saying 2 pi minus theta. And then in the third quad we have 180 degrees plus theta. That's like saying pi plus theta in radians. Then in the second quad we have 180 minus theta, almost root pi, and it's going to be a pi minus theta. And in the first quadrant we don't have any reductions available, so a tan pi plus a, this is in the fourth quadrant, and in the third quadrant, and in the third quadrant tan is positive, so solving this by reduction, it's going to be a plus tan a like this. 4.1.2, they now want us to simplify that expression. So this is going to be equals to, okay, let me not rewrite it, but let's just go straight to simplifying. So this has already been solved on the previous question. It's what? It's tan a like this, multiplied by, now for the second part, this is a cos 180 minus a in the second quadrant. We see this in the second quadrant, and in the second quadrant only sign is positive, so it means that cos is going to be negative, so it's going to be negative cos a multiplied by 360 minus sine 360 minus, it's where? Fourth quadrant, and in the fourth quadrant it's only cos that is positive, so we have that. And then for the one on the denominator we're gonna have a sine. Okay, interesting. In fact, in the first quadrant we do have, but that's if you went past the revolution, right? So in the first quad we also have another reduction formula, that is 360 plus or 2 pi plus a like this, or theta. Let's use theta for consistency like that. So in the first quadrant we have what? All the ratios being positive, so a sine 2 pi plus a, that's going to be a plus sine a like this, equals to, and then, or let's check, let's see. Okay, so I can just cancel these things out. I can just cancel these two out, and let's work it out like this. A negative times a negative, that's what? That's a positive. And then the sign cancels out the sign. We are now left with what? With just the cos and tan. So that's going to be tan a multiplied by cos a. That is what is left. And we need to convert the tan, right? The tan is an identity. We can change this to sine a over cos a multiplied by cos a over 1. This cancels out. I'm now left with only sine a. Okay, surprisingly this is a short question. Okay, so cos squared x minus cosec squared x, complete the identity. So for 4.2 this should be equals to negative 1. 4.3, easy mark guys, easy mark. Okay, now we are proving an identity. For this case we're going to take the complicated side. Yes, the complicated side, it's this, the left hand side. So we're going to take the left hand side, in this case LHS, left hand side, that is sine x plus cos squared x multiplied by cosec x. This is equals to sine x plus cos squared x and multiplied by, so we change this to its inverse, which is sine x in this case, equals to sine x plus the cos times the 1, we get a cos squared x over sine x. Then divide this by 1, and then we apply the butterfly method. Okay, the butterfly method, what it simply, okay, how it works is, if you have two fractions, this is fraction 1, fraction number 2, I have fractions with different denominators, right? So what I'm gonna do, I'm just gonna take this, multiply it by that. If you have fractions with different denominators, we apply the butterfly method. However, if the denominators are the same, you're just gonna add or subtract the numerators depending on the sign in between those fractions. So since the denominators are not the same, I'm multiplying sine with sine, I get a sine squared x plus the 1 times cos, that is cos squared x, and then we divide by 1 times sine, that is sine x, equals to, there's an identity of 1, sine squared plus cos squared gives us 1 over sine x, so the final answer is just gonna be cosec x. That is the final answer, and concludes our question 4. Now for the question 5, I think we're gonna need a grid for this one. Okay, so this is question 5. I think what I should do is go grab the grid on the answer book so that we can answer the first question, 5.1. Here's the grid. Let's go back, and I think let's paste it here or here. Why not? Yeah, let's put it here. Now we have to plot the graphs of f, which is cos x minus 45 degrees, this one, and we have another function g, which is minus 2 sine x, where the graph is plotted between 0 degrees and 360, between 0 and 360, okay, and 360. So they want us to draw the graph of f and g on the same set of x's provided in the answer book. This is what we have. The easiest way to plot a trigonometric function is actually to use your calculator. If you have the Casio 82ZA plus 2, it's gonna work just fine as well. So we say what mode? Yeah, press mode. No, shift, no. Oh, table. Okay, so we start off by pressing mode, and then we go to table, and then you see an f of x appearing there. So we're gonna punch in that function, the cos, then you're gonna say alpha x to put in the x, minus 45 degrees, you close the bracket, you say equals to, then g of x, it's minus 2 sine, again you press alpha, and then you look for x. X is found where there's a closing bracket up, just below the button for sine. So you press that button after pressing alpha. You press alpha, then you press that button, you're gonna get an x. You close the bracket, equals to. Okay, start. Where does the graph start? It starts at 0, equals to. End. Where does the graph end? It ends at 360 degrees, equals to. Step. Okay, the step, it's normally gonna be found on the grid that is provided. Look, 0 to 45, 45 to 90, 90 to 135. There's a step of 45 degrees, meaning there's a difference of 45 degrees for every angle that is marked down on the x-axis. Okay, so for the step we're gonna use a 45 degrees. 45 equals to then you get your table for f of x and g of x. So you're just gonna plot now. So for 0, okay, that's marking. Now let me use purple for g of x. Let's start off by plotting g of x. So for g of x, I get a 0 degrees for 0 degrees. And then for 45, I'm getting a minus 1.4. So a minus 1.4 is around somewhere here. And then the 90 degrees gives me a minus 2. Remember, we are plotting the purple, the green, the g function. And then 135, it's the same, or should be in line with that, because it's 135 and minus 1.4. So somewhere along this line. And then we have 180 degrees. The 180 degrees, that's 0. And then the 120, the 225 the 225, that's positive 1.4. 1.4 is around here. And then 270, that's 2. 270, that's 2. 315 should be in line with this point on 225. And then we have 360 at 0, like this. And then we connect all of these points to give the graph of G like this. Don't use straight lines. Use curves, okay? Curves. We are trying to connect the points by in that process trying to construct something that looks like a mountain. So we have a trough, and then a peak, and then a peak, and then a peak. So this is G. This is G. Now let's plot f of x. F of x, why not? Let's start here. So I'm gonna use orange for that. So 360, 0.7, positive 0.7, positive 0.5, 0.7, could be somewhere around here. 315, that's 1. No, 315, that is f of x. Okay, it's 0 degrees, it's here. And then 270, that's negative 0.7, negative 0.7, somewhere here. And then 225, that's negative 1. 225, that's negative 1. And then we have 180, which is the same line as this. And then 315, that's 0. That's 0. Then 90, it's around here. And then 45, that's positive 1. And then 0 degrees, it takes us back here. And then we're gonna have a graph that looks like this. Like this. I'm just connecting. Okay, then f, that is the orange function. Okay, 5.1 done. 5.1 done. Now remember, plotting a function or a graph of a trigonometric function, just use a calculator, man. Stress free. Okay, this is done. We are doing question 5. Then 5.2, write down the value of x for which g is a minimum. Okay, g is a minimum. Where g is a minimum? Now let me use a marker that is green. I'm gonna show off the maximum point using green for both graphs. So this is G, that's maximum for f as well. All right, that's maximum. Now we're gonna have minimum points. Minimum points are where we have a turning point just below the x-axis. Okay, so since the question is asking for the x value of g, which we get a minimum, so we see that a minimum for g, it's this point. So the x value for that minimum, it's gonna be 90 degrees. So the x value where we get the minimum, it's x equals to 90 degrees. 5.3. I don't need to divide the paper because it's gonna be a short question anyway. 5.3. Write down the period of g. Write down the period of g. Okay, so let's use blue this time as a marker. Okay, black, let's go back to this. Okay, so how do you measure a period on the graph? A period is measured like this. Your graph needs to have a trough and a peak. So where the graph stops after creating a full complete wave with both the trough and the peak, where it stops, where it ends, that's where you get your period. So based on what we see, we can say the period for graph G, that period, it's gonna be 360 degrees. All right, but now I have another question for you. Maybe try answering this one on the comment section. What is the period of the f function? What is the period of the f function? Let me know in the comment section. 5.4. Use letters A and B to indicate whether graphs this is equals to that. Looks kind of weird, but okay. We have this minus 1 over 2 cos x minus 45, x minus 45, x minus 45 degrees. Okay, hang on, there we go. Minus 45 degrees is equals to sine x. Okay, so I know where the sine is coming from. I know where this is coming from. It's coming from that g function. The cos x minus 45, it's coming from that orange function. Okay, so what should happen is that we need to sort of like reconfigure that equation so that we can actually see what is actually happening. Or but if you can see it, let me say it's where the graphs are intersecting or where the graphs are equal, right? But it's safe to do this. Multiply by a minus 2 over 1 on both sides. Minus 2 over 1, cancel, negative times negative, it's positive. Then we're going to end up with the cos x minus 45 degrees. This is what I was looking for, to reconfigure the equation so that you can see that on the left hand side we have f of x, and then on the right hand side we have minus 2 sine x. Right, so in other words, we are looking for the parts of the graph where f, that's f, is equals to g of x, that is g of x. So we are looking for those parts of the graph where f is equals to g, where the graphs are equal. It's at these points, at this point, points of intersection. So we need to use letters A and B. So this is A and then this is B. This is B. Or you can start with B, then follow that up with A. It doesn't really matter. It doesn't really matter. Okay, so this is where the graphs are equal. 5.5. Use the graphs drawn in 5.1 to determine the values of x for which f prime x is less than 0. Okay, here's something you need to understand. The f prime actually represents a gradient of a tangent, or the first derivative, if you may. So the gradient of a tangent, what is a tangent? A tangent, it's a line that touches a curve at only one point, right? So we are looking for those parts of the graph where the derivative or the gradient of the tangent is less than 0, right? Where the gradient of that tangent is less than 0, meaning it has a negative gradient. I think I was explaining this back in question 1, yeah, the first question I did, that if your line is slanted like this, it's gonna have a negative gradient. If it's slanted like this, it's gonna have a positive gradient, like this. If it's slanted like this, it's gonna have a positive gradient, or an f prime x that is bigger than 0. Like I said, f prime represents a gradient, a derivative represents a gradient. Then you also have a m that is less than 0 for a line that is tilted like this, f prime less than 0. So if I were to follow up tangents, or try to sketch tangents along the f function, that's gonna give me a line that is slanted like this, So if you take a look at this, if I draw a tangent, say maybe here, I'm gonna have a line that is slanted like this, right? So this is a positive gradient. So it means that along this green part of the graph, whatever tangent that I try to sketch, it's going to have a positive gradient. Along this part of the green part of the graph, whatever tangent I'm going to try to draw, it's going to have a positive gradient, a line that looks like this, a tangent with a line that looks like that. However, for this part of the graph that I'm highlighting in purple, it's gonna give us lines or tangents that are slanted like that yellow line. So the gradient is gonna be negative. So it's gonna start where? So we are looking for the x values for which this is true. For which that is true. Let me go back to writing mode. Okay, so it starts at 45 and ends where? At 225. So the answer for this is going to be x element of, we exclude the 45 and exclude the 225 as well. We exclude the 45 and the 225. It starts at 45, but the 45 is excluded, and ends at 225, but they are excluded. Why? Because at 45, that's where we get a turning point, and a tangent has a 0 gradient at the turning point. At 225, the gradient has the tangent has a 0 gradient at that turning point. So the solution for this should be this 5.5. It's x element of 45 degrees to 225. All right, now we jump to question 6. It's another question on trigonometry. All right, so the question reads as follows. The diagram below shows a cyclic quadrilateral TSMR, a piece of information that is very important, very important. Okay, it's a cyclic quad. Keep that in mind. Okay, keep that in mind. TS is 22, TR is 18, and then we are given an angle T as 67 degrees, R1 that is 42.5 degrees right here. Okay, then for 6.1 they want us to determine the length SR. Okay, so the principle is whenever you calculate sides or angles in a triangle, we use trigonometry. But if the triangle is not a right angle triangle, you cannot use SOHCAHTOA. You'll have to use triangular formulas, or what are they called? The sine rule and the cosine rule, as well as the area rule if you are asked to calculate the area. Let me repeat. If you are given a triangle to calculate a side or an angle, and that triangle is not a right angle triangle, you'll have to use the sine or the cosine rule, or the area rule if you have to calculate area. So you can see that none of these triangles are right angle triangles. Okay, so they want us to calculate SR. So SR, in order to calculate SR, we'll have to rely on this triangle. Okay, let me tone it down and say we're gonna have to use this triangle TSR, and that big shade represents SR. So that's the length we need to calculate. Now look, I'm given side TS is 22, I'm given side TR is 18, and an angle between those two given sides. We're gonna have to apply the cosine rule. All right, so this is 6.1. Do I don't know, but let's do it anyway, dividing the page like this. So this is 6.1. We want to calculate SR, so we're going to use the cosine rule. So SR squared is equals to TR squared plus TS squared minus 2 TR multiplied by TS multiplied by cos of angle T. Therefore SR squared is going to be equals to TR, that is 18 squared, plus TS, that is 22 squared, minus 2 TR, that's 18, I'm just substituting, and TS, that is 22, multiplied by cos of 67 degrees. Cos of 67 degrees. And then we're just gonna punch this on the calculator. Let's punch this on the you know what, let me just do this instead. Do this. Just go straight to finding the answer. So I'm gonna punch the whole thing. Whatever answer I get, I'm gonna take the square root. Okay, compile. Then we're gonna say square root of 18 squared plus 22 squared minus 2 times 18 times 22 times cos 67, and then the answer is gonna be 22,34 in 2 decimal places. Yeah, 34 meters in 2 decimal places. Now they want us to calculate angle M for the next question. This is 6.1.2. So angle M is gonna be equals to 180 degrees minus 67 degrees is equals to, I'll give a reason as to why. 113. Why are we doing this? It's a cyclic quad. From Euclidean geometry we know that opposite angles in cyclic quad are what? Are supplementary. They add up to 180 degrees. They are supplementary. That is why I subtracted 67 from 180. Supplementary means that the angles add up to 180. 6.2. Answer the following questions with regards to triangle SMR. Let's move away from that triangle now. We're now shifting our focus to a new triangle. Let's call it, okay, they call it SMR. It's this one, SMR. SMR, that's SMR. Okay, complete the sign rule. SM, where's SM? SM over R1 is equals to SR divided by, it should be divided by sine M. So the complete rule looks like this: SM over sine R1 equals to SR. This is the answer now. This is the answer. It's sine M, angle M. It's sine angle M. That's the 1 mark. That's 6.2.1 and then 6.2.2. Hence determine the length of SM. So we're going to apply that. Remember, we have 113 degrees. Do I have, oh, we want SM. We just calculated SR. SR is 22,34 meters. Yeah. So I have this length and its opposite angle. I don't have this length, I'm putting a question mark, but I have its opposite angle. So SM divided by sine R1. Let's do this. Sine R1, that's 42,5 degrees is equals to SR. Come on, that's 22,34. And then we divide by sine M. Sine M, it's that 113. Okay, yeah, it's easy to mix up things here. Sine M, SM, they almost sound the same. And then we're gonna just cross multiply. And then after cross multiplying, we're gonna end up with a 22,34 multiplied by sine 42,5 degrees, everything divided by sine 113 degrees. So that is SM equals to, then we calculate 22,34 multiplied by sine 42,5 and sine 113. I get 16,40. 16,40. This is rounding off to 2 decimal places. 40 meters. Hey, SM, you're gonna cause troubles. Okay, so then for the last question, the area of triangle SMR must be fertilized. That red area must be fertilized. 1 bag of fertilizer covers this much. Determine the number of bags of fertilizer needed to cover that area. So the logic goes like this. We'll have to find the total area. We'll have to find the total area to be covered. In other words, we'll have to find the area of that red triangle. After finding the area, we're going to divide by the area covered by 1 bag of fertilizer. The answer we get after dividing those 2 areas, it's going to tell us how many bags are required. So I have SM, right? I just calculated SM. It's 16,43. Okay, I get it. Now I have this length. I have that length, the length of 22.34 and the length of 16.40, and in between these 2 lengths I'll need to have the angle between these 2 lengths, meaning that I'll have to find S2 as well, right? I need S2 because it works very much the same way as the cosine rule, where you need a length and a length, and between those two lengths you need the angle in between. So let's calculate S2 before we can calculate the area. Or let me just say, for 6.3, in order for us to calculate the area, given the status of the information that is presented to us, or the information that we have around this triangle, I have this side and that side. It means that I'll have to use SR and SM in my calculations. So triangle of SMR, let me say area of triangle SMR is equals to half multiplied by SR multiplied by SM multiplied by the sine of the angle in between. So that's gonna be S2 equals to, so we're gonna say a half multiplied by, what is SR? That's 22,34. SM, that's 16,40 multiplied by sine. S2 we don't have, but we can calculate sum of angles in a triangle. What is that giving us? Let's check. So that's gonna be 180. Let me just calculate that here. S2, it's 180 minus 22,34 minus 16,40 equals to, that's 22,34 minus 16,40. Whoa, okay. Where did I get? Oh, look, I'm subtracting the lengths instead of the angles. So that is 42,5 minus 113. Okay, that is 42,5 minus 113. I'm getting 24.5. And the answer is 24,5. 24,5 is the angle here. And then we calculate the area. Half times 22,34 multiplied by 16,4 multiplied by sine 24,5. I'm getting 75,97 meters squared. Therefore, the number of bags for this fertilizer is going to be equals to the total area 97 divided by the area covered by one bag of fertilizer, as that. So we're gonna say 75,97 divided by 15,178. I'm getting 5,005, but we are looking for the number of bags. I cannot have 5.1 bags. It should be a whole number, so I'm rounding that off to the nearest whole number. So it's gonna be 5 bags that are required to fertilize the whole area of that given triangle. Okay. Where's that thing? I hope, of course, yes. Okay, now we are now over trigonometry. Now we are jumping to something different. Yeah, Euclidean geometry. All right, now this question, it says in the diagram below, O is the center of the circle. R, S, V, and W are points on the circle, so they lie on the circumference. R, S, and V and WV are produced to meet the T. What's that? Okay, RV and WS intersect at P. and we are given SRV as 20 degrees and ROW as 80 degrees. Okay, the only thing that I can highlight as being important is this part right here, O as being the center, because there are theorems that rely on the center, right? They work with the center. Like for example, there's a theorem that says angle at center is equals to 2 times angle at circumference. Exactly. So O is the center. That's an important piece of information to know about. Okay, so going back to writing, so this is question 7. Finally, we are doing something different from trigonometry. It was getting too much now. Okay, so we have question 7.1.1. I'm not going to divide the page this time. I think we don't have a lot of questions, and the calculations are not that big for this one. Okay, so we want V1. V1 is this angle right here. Okay, so V1, which theorem do we apply? I'm gonna highlight the diagram like this just to show that how the 80 degrees and the V1 relate to each other. So when approaching Euclidean geometry problems, just look at the information that is given to you. Use that information to calculate the unknown width. In this case, the 80 degrees and the V1, it makes sense to start with that. Like, there's a relationship that exists between the 80 and the V1. It's an angle at center, this one. This one is an angle at circumference. And we know from theorem, I think 2, angle at center is equals to 2 times angle at circumference. So this 80 is equals to 2 times V1. Reason, angle at center equals to 2 times angle at circumference, 2 times angle at circumference, like this. And then we're going to divide both sides by 2, divide by 2. Therefore, V1 now becomes equals to 40 degrees. There we go. Is equals to 40 degrees. Now we have to calculate angle T, this angle right here, this angle right here. Okay, let me clear up the diagram. Again, you're gonna look for ways you're gonna look for ways to find a relationship that exists between 80 and T. If no theorem can be applied between the 80 and the T, skip to the next angle. What about 20 and the T? Now, one might argue saying that if we had V2, we were going to be able to calculate what? Angle T. Oh, but you still remember, we calculated what? V1 just now, right? It's 40 degrees. So the V1 and the V2 are angles on a straight line. So we can calculate V2 first and work out angle T by using angles in a triangle. So for 7.1.2, we can say the V1 when added to the V2, that gives us 180 degrees, right? Angles on a straight line. Angles on a straight line. So V1, that's 40, plus V2, that is 180. Therefore V2, that is equals to 180 minus the 40, the V2, that is 140 degrees. That's the answer we got for V2. Now we're going to use sum of angles in a triangle. In this triangle in particular, the RVT triangle, to work out the angle for T. So therefore we're going to say angle T plus the V2 plus the angle the angle, interesting, 20 degrees S. Okay, the angle SRV is equals to 180 degrees. This is a sum of angles in triangle. Sum of angles in triangle. I don't have T. I'm leaving it as it is. V2 I don't have. I have. It's 140 plus SRV, that is 20 degrees, is equals to 180. Therefore angle T is equals to 180 minus 140 minus the 20. Angle T, that is equals to, let's go, 180 minus 140 minus 20. I'm getting 20 degrees. That is 20 degrees for T. Then for the last question, we get we are asked to show with reasons that SPVT is not a cyclic quad. Okay, we are actually doing the opposite now. In many cases, they ask us to calculate or show that a shape is in fact a cyclic quad, but now it's the opposite. Alright, so they want us to show that this shape is not a cyclic quad. We just calculated T. We got 20 degrees, right? We got 20 degrees. And then if, say, maybe I calculate P4, if I calculate the P4, I can use the theorem which states that angles in a cyclic quad, the opposite angles in a cyclic quad are supplementary. So if I calculate P4, then say maybe I get an 80 degrees. You can see that an 80 degrees when added to the 20 degrees is not giving us 180. So by opposite angles being supplementary, the opposite angles in a cyclic quad should add up to 180. So let's calculate P4. If the sum of the angle between P4 and T, when added, they don't give us 180, it's not a cyclic quad. That's the idea with this. Okay. So, but first we'll have to calculate P4. What angles do we have? This is V1. We got 40 degrees. Okay, 40 degrees. I just need to calculate P4. Alright, I see. There's a bow tie here. There's a bow tie. Let me show you. Let me use a red. There's a bow tie. This is the bow tie. This is the bow tie. This is a bow tie. Okay, so this means that the R1, I mean the S1, this S1 is equals to that V1. Now, what does the S1 have anything to do with the P4? You'll see, don't worry, you'll see. Angle S1 is equals to 40 degrees. Both equals to, I mean the S1 is equals to the V1. They are both equals to 40 degrees. Why? These are angles in same segment. Angles in the same segment. That's a 40 degrees. So here we get 40 degrees. 40 degrees. Therefore, the P4 angle is equals to 20 degrees. Which 20? This 20 plus that 20 plus that 40, which is S1. This S1. When we add this 20 and that S1, we're gonna get a P4. Why? It's an angle in, okay, it's the exterior angle of triangle. Exterior angle of triangle. So this plus this gives us what? 60 degrees. 60 degrees. I now have P4. Now we can test if that shape is a cyclic quad or not. Therefore, P4 added to T, it's 60 plus 20. I'm getting an 80 degrees instead. 60, 70, yeah, I'm getting 80 degrees instead. Therefore, since the P4 plus the angle T are not equals to 180 degrees, it means that SPVT is in fact not a cyclic quad. It's not a cyclic quad. It's not a cyclic quad. So that is how we show that a thing is not a cyclic quad. Okay, next question, question 8, another Euclidean geometry question. 8.1, and the diagram below O is the center of the circle. It's the center of the circle, so I'm just gonna highlight. Okay, let's bring back that big marker. Okay, so O is the center of the circle, important. Tn is a tangent, important to the circle at A. So that is the center, and then we have this tangent, and then we have parallel lines. So CD is parallel to Tn. We are also given that angle 46 degrees, A4, and C1. But I'm just highlighting the key phrases or the key pieces of information. CD parallel to that. Parallel lines, keywords or key piece of information. Parallel lines, you think in terms of fun angles. 2, you have a tangent. There's a theorem that involves a tangent. A center is presented to you. Think in terms of that theorem that involves a center. Something like a radius gets mentioned. There are theorems that involves radiuses, making use of radiuses. So this is not mentioned, but it can be observed from the sketch. You can see that we have a radius here. Radius in green. Here's another radius in green as well. This is gonna come in handy. A radius, highlight. A tangent, highlight. A center, show that. Parallel lines, keep those in mind. Do I need to divide a page? Nope, I don't think so. So we are doing question 8. Question 8. So 8.1.1. They want us to calculate the angle for BCA. So they want us to find this angle BCA. That is BCA. So BCA is in fact equals to that 45 degrees. That's a tan chord theorem. So this is equals to that. So BCA is equals to 45 degrees. That is a tan chord theorem. That is a tan chord theorem. So the angle C as a whole, this one is equals to that 46 degrees as a whole. Angle A3, 1.8.1.2. Okay, so angle A3, it's this angle right here. Okay, it's that angle right here. So the green radius OA and that tangent Tn, they are perpendicular to each other, right? There's a theorem which states that. So let's start off by saying angle OAT. Angle OAT is equals to 90 degrees. How do I know that the angle is equals to 90 degrees? I know this because radius is perpendicular to a tangent. That's one of the theorems in Euclidean. So therefore, if we have this angle to be 90 degrees, I can now calculate A3. So therefore A3 is going to be equals to 90 degrees minus 46 degrees. So that's 90 minus 46. I'm getting 44 degrees. So that is 44 degrees. That's A3, A1. A1, for how many marks? 2 marks. Okay, so that is 8.1.3. This time around we are looking for A1. Right, okay, not so obvious, but let me perhaps highlight this. Okay, A1. Okay. Oh yeah, it is. This, that, and this, right? They are alternating angles. So the angle A1 is alternating with this entire angle right here. So it's that 20 degrees plus this 46 degrees, right? That 46 degrees. So I can say A1 is equal to DCA, to angle DCA. Why are they equal? It's because of their alternating angles. Therefore, the A1 is going to be equals to 20 plus 46, which gives us a 66 degrees. That is the answer. 8.1.4, we are looking for angle O1. Okay, 3 marks. That's rather interesting. Okay. 66. You know what? Let's just clear up the sketch. It's so much noise. It's noisy. So this is 66. Maybe let me put this information here. And then this is 46. What else did we calculate? A3, we got 44. I don't have A2. I'm looking for this now. All right, maybe a bit of highlighting here. This is a tangent, yes? That tangent in relation to this shape, which is the triangle inside the cyclic quad, the triangle inside the circle. Now, this 66 is equals to that angle B. That's what? Tan chord theorem, right? So if I had B, I'll be able to calculate O1 because that's an angle at the center and that's an angle at the circumference. So let's calculate B and then we're going to calculate OA. Okay, so angle B is equals to angle A1. They are both equals to 66 degrees. That's through the tan chord theorem. B is equals to angle A1. Therefore, angle O1 is equals to 2 times angle B. Why? Because of angle at center is equals to 2 times angle at circumference. Therefore, that means O1 is going to be equals to 2 times 66. That's 132 degrees. That is the final answer, O1. Jumping to 8.2, another circle. In the diagram below, D, H, G, F, and E are points on the circumference. HG is extended to K. D1 is equals to 48, HG is equals to FG. So these are the equal lengths. Equal. So we have equal lengths. Okay, then we are given this piece of information. What else is important? We don't have a tangent. Yes, we don't have a tangent. However, we do have a cyclic quad. Maybe let me highlight that in green. It's gonna come in. Yeah, that's gonna come in handy. That's gonna come in handy. All right, so this is a cyclic quad. Sorry, that is a cyclic quad. I see a bow tie as well. I can see a bow tie. This one. This one. Is there another one? Yes, there is. Okay. I think there's several bow ties here. There's several bow ties. Let me just remove that, the green. So just to reduce the noise on the diagram. Now let's make it black and start answering questions. 8.2.1, we need to calculate angle E. Okay, I see. Angle E is going to be equals to 48 degrees. It's going to be equals to 48 degrees. Remember what I said? Whenever you approach Euclidean geometry, just ask yourself questions, a set of questions. Like, before answering a question, highlight the keywords or the key most important information, your radius, your tangent, equal lengths, whatever angle is given. Then you need to use those given angles to calculate the unknown. So how do we use the 48 to calculate E? You saw that bow tie the green bow tie that I drew. It's telling us that E is equals to D1. They are both equals to 48 degrees. Why? It's because of these are angles in same segment. Angles in the same segment. Angles in the same segment. So that's 48. Then D2. Remember, there's 48 here. Then D2. Where's D2? Oh, D2. There we go. D2. So 8.2.2 D2. Okay. These two equal lengths, they subtend the same or equal angles at a given point. So take a look at D1. D1 is at the circumference and it's 48 degrees. D2 as well, it's found on the circumference. So that means it's going to be equals to 48 degrees as well. So the D2 is equals to 48 degrees. Why? It's because of these are angles subtended by equal chords, right? Angles, or let's say equal chords subtend equal angles at circumference. At the circumference. There we go. 8.22. G4. Last question on question 8. G4. Okay. Yeah, so this red shape is a cyclic quad. So G4, that means it's going to be an exterior angle. 8.2.3. That G4, it's going to give us an angle of D1 plus D2. This is an exterior angle of cyclic quad, of a cyclic quad. So therefore G4 is equals to D1, that's 48, plus D2, that's also 48. So 48 plus 48, that's 96. That is 96 degrees. Okay, so that's our question 8. That's our question 8, Euclidean geometry. Let's take a peek at question 9, another Euclidean geometry question. Okay, the question is a two-part question. We have 9.1 and 9.2, which involves proportionality, and we also have the midpoint theorem in 9.1 within a circle. Okay, but still under the context of Euclidean geometry. 9.1, in the diagram below, O is the center. Bingo. We highlight. Let's get a bigger one. O is the center of the circle. Then we are given OM. OM, would this be a radius? Of course not. That's not a radius, but it's just a line. That is OM equals to 3 centimeters and bisects AC. Oh, I see. That's theorem 1. A line from center and bisects a chord. A, B, C are points on the circle such that AB, that entire length AB, is equals to 10 centimeters. And we have another piece of critical information. Parallel lines. We have this line being parallel to that line, and then M is the midpoint of AB. Right, that's midpoint theorem in that triangle ABC. But let's see what sort of questions they have for us. Now question 9, and then for question 9 we have 9.1.1, where they are asking us to write down with reasons the size of angle M1. Like I said, this is theorem 1, so M1 is equals to 90 degrees. That's going to be equals to 90 degrees. Reason, it's line from center to midpoint of chord, isn't it? Line from center to midpoint of chord. So that line AB is a chord of that circle. Determine the length of the radius of the circle. Nice. Okay, so let's draw maybe a dotted line like this. A dotted line like this that connects B and O. So since this is 90 degrees at M1, it means that triangle MBO, it's gonna be what? That's gonna be a right angle triangle. So in triangle MBO, we wanna calculate the length BO, which is the radius, by the way, Now, since this AB is equals to that MB, it's given, right? MB is equals to AM. They are both equals to 10 divided by 2, which is 5 centimeters. Okay, so I now have the length of MB that I can use to calculate BO through the Pythagoras theorem, right? We have a right angle triangle anyway. So OB, which is the radius, is equals to MO squared plus MB squared is equals to, what is MO? That's 3. What is MB? That is 5. Equals to 9 plus 25. 9 plus 25. So 25 plus 9, that is 34. Which is simply OB, then taking the square root, then we get an OB that is equals to, okay, let's round it off, why not? 34 is equals to 5,83 centimeters. So that is the length OB. If MN is equals to 5.12. Write down with reasons the length of BC. If MN, that short length, is equals to 5.12 centimeters, what is the length BC? So for 9.1.2, BC is equals to 2 times the MN. The MN. Why? It's because of the midpoint theorem. That is the midpoint theorem. Alright, that's the midpoint theorem. You have this being equals to this, and you have lines that are parallel. That's clearly a midpoint theorem. So BC is going to be equals to 2 times MN, which is that 5.12. So multiplying gives us a 10.24 centimeters. That's our answer for 9.12. All right. Then we jump to the 9.2, the second part of the question, where we have in the diagram below, ABCD is a right angle triangle. So that big triangle on there, the big triangle, that's a right angle triangle. This, this green triangle ABC, that's a right angle triangle. That's a right angle triangle. Now they want us to, okay, before going to the proving and answering the questions, let's check what sort of information we are given. We have 90 degrees, which is this angle, AD being perpendicular to BC. AD being perpendicular to BC, we have another 90 degree here, and then we have parallel lines, and then we have a ratio between two sides, CE to EA. Let's mark that down, CE to EA. We have a ratio of 2 and 1. Perfect. Nice, very nice. Okay, therefore we have length BC. Now keep in mind, the 1 and 2 are not actual lengths. They are not actual lengths. The 1 and the 2, this ratio here, they are not actual lengths but ratios. Okay, ratios. So 9.2.1, prove that triangle ADC and BAC are similar. Let me mark down, it's what? It's ADC. Hang on. Or ADC. So it's the green triangle and the red one. We need to prove similarity for those two. Okay, so ADC. First of all, we know that okay, let me start off by saying D3 is equals to 90 degrees. This is given, right? Therefore, this would automatically mean that angle ADC is also equals to 90 degrees. I have 90 degrees and I also have angle A that is equals to 90 degrees. Therefore, this means that angle A is equals to ADC. They are both equals to 90 degrees, right? This angle is equals to this angle D1. No, not D1, but ADC. They are both equals to 90 degrees, okay? Then we have that common angle C. So angle C is part of the green triangle, and the angle C is also part of the red triangle. So they are both, the angle C in the red and the angle C in the green are equal. So that's a common angle. Reason, it's because of that's a common angle. right? So I have the first two angles being equal, and the next two angles being equal, and then we're gonna have um, which angle? Okay, okay, we're gonna have then a 2 being equals to angle B. This is the third angle of triangle. This being equals to that angle. So when proving similarity, you need to show that all of the three angles on each triangle are equal. That they are equal. So A2 is equals to angle B. Okay? Therefore, we're gonna say triangle ADC is similar to triangle BAC, like this. How did we prove this? We proved it through an angle. We used three angles to prove similarity. Okay, that was 9.2.1. 9.2.2. Show that AC squared is equals to DC over BC. Alright, so again, proving these equations, more especially involving the sides of one of the triangles. Like for instance, we are proving that AC squared is equals to DC times BC. The length DC is right here. The length BC is the total length of that green triangle. The line AC is common for both triangles. So these lengths are also found in the triangles we were proving similarities for. So once we have proved the similarities, it means that the corresponding ratios of the sides are gonna be equal. We're gonna use this. AD divided by BA or AB is equals to DC divided by AC, and then AC is equals to it's divided by BC. Why is this true? It's because of triangle ADC is similar to triangle BAC. That is why we have these ratios. Okay, so out of the three ratios, we need to pick two that's going to allow us to calculate that AC squared equals to DC times BC. There's DC. This is DC. DC is also part of that equation. There's BC. BC is also part of that equation. Then there's AC and AC. And there's AC over there. So we're just gonna have to pick this ratio and that ratio number 2. So we're gonna say DC over AC is equals to AC over BC. Then we cross multiply, we get an AC squared. We cross multiply, we get a BC multiplied by DC, which is the same thing as that. 2 marks. I hope everything is gonna fit in here. 9.2.3. Then we have A, complete the statement and reason. DC over BC is equal. all right. So now we were proving similarity, right? Like I said, this question 9.2 involves proportionality. Let me clean this up. Let me just clean it up like this. All right. So the question says, look at DC. There's DC. The DC is divided by BC. There's BC. Equals to CE. there's CE. It's going to be divided by AC. So we should be dividing by AC right here. So we should be dividing by AC because it's a proportionality theorem. The reason, what's the reason? The reason is because of the proportionality theorem. It's because of the proportionality theorem. That is the reason. That is the reason. Due to the fact that AB is parallel to DE, like that. Determine the length DC. They want us to calculate the length DC. That's length DC. Okay. We shouldn't forget that the ratio for this length is 1. The ratio for this length is what? It's 2. So we're gonna say, excuse me, so therefore we're gonna say B. I've answered A on that question paper, so then B, it's DC over BC equals to CE over AC. We're definitely gonna have to use that formula. We have no choice. So DC it's 12 over BC. Sorry. So DC is not given. It's BC instead. BC it's 12 equals to CE. CE, okay, we're gonna use the ratios here. So this is gonna be CE, which is 2, divided by AC. AC, it's that entire length, so it's gonna be the 2 plus 1. We're gonna have a 3 right here, right? We're gonna have a 3. This we are taking from that, okay? We're taking from that, the previous question. So therefore we cross multiply, we end up with a DC times 3 equals to 12 times 2, and then we come back and divide by 3 like this. They cancel. DC is equals to 12 times 2 over 3. I'm getting an 8 centimeters. I'm getting an 8 centimeters. And then they want us to calculate the length of AC. So the above, the 9.22, we're gonna use that formula to calculate AC. I do have BC, yes. BC I do have. Yeah, BC it's the 12. DC it's the 8 that I just calculated. So for C, we're gonna use this DC times BC. DC it's 8 times BC it's 12 AC squared, and then AC take square root times 12. Then the answer is gonna be 4 square root 6. So this is the answer for AC, unless they want this rounded off. 9.78 centimeters. So this is the answer for the 9.2, which concludes the question 9. Ta-da! On to another question. Question 10, which involves something totally different now. Right, in this question we are presented with a picture and a diagram below showing the rear wheel of a training bicycle. You know, those bicycles that you find in the gym, and the rim has a radius of 26 inches and a thickness of the tire is 24 millimeters. Now take note, These are units of measurement. The millimeter is a unit of measure. In this case, it was used to measure the thickness of the tire, right? And then we have a 26 inches, another unit of measure. So it's two different units of measures that were made. The first one was for the radius, 26 inches, and the other one is for the thickness of the tire. For the first question, 10.1.1, they want us to convert the 26 inches to meters if 1 inch is equals to that. So 1 inch is equals to 0.0254 meters. 1 inch. I need to convert 26 inches. So 26 inches to meters. The 26 inches to meters. We're gonna have to do the following. We take the 26, we multiply by the number of meters per inch, 0.0254. We multiply 26 times 0.0254 equals to 0.6604 meters, but we are rounding off to 2 decimal places, so that's going to be 0.66 meters. That is for the radius of the rim, so it's the distance from here to there. Let me use red to highlight. Okay, I'm just re-emphasizing. Yes, it's shown on the diagram, but I'm just re-emphasizing. So it's that red length from the center to the inner lining of the tire. Okay, so that's the radius, 0.66. Next question. For the next question, they are asking us to calculate calculate in meters the diameter of the wheel, which includes the tire. So what we are asked to calculate is now the diameter, right? What is the diameter? A diameter, it's the length that goes across the circle through the center from circumference to circumference, or we can basically say it's a chord that runs through the center of the circle. So it's a diameter. So that red length is the diameter. Okay, that is the diameter. So to calculate the diameter in this instance, we're gonna say diameter is equals to okay, all right, let's count it like this, or calculate it like this. From here all the way to the center, we know that to be 0.66. From the center again all the way through to the other end like this, it's 0.66 as well, right? So it is safe to say 0.66, we multiply that by 2, so this and this, or you can just say 0.66 plus 0.66, but I'm just going to multiply by 2. So it's this plus this. Now the missing part of the calculation is the thickness of the tires. Remember, the diameter was measured from this point all the way to that point, so it includes the thickness of the tire. So the thickness of the tire, it's that plus, remember the thickness is 24, so that's going to be 24 multiplied by 2 again, right? Multiplied by 2 because we have 2 instances of the thickness that passes through in which the diameter passes through, the diameter length passes through. So it's the tire length, width and the tire width. So it's the 24 multiplied by 2. Keep in mind The 24 is in millimeters, and the question says calculate in meters. So I need to also divide by 1,000 so that I can convert what? So that I can convert the millimeters to meters. Ne? So 0.66 times 2 plus 24 times 2, divide that by 1,000. I am getting a 1.37 meters in 2 decimal places. That's the diameter. Then for the 10.1.3, if the circumferential velocity of a particle on the outer edge of the wheel is this, that's the circumferential velocity. Determine the rotational frequency of the wheel in revolutions per second. You can see that the velocity is given to us in kilometer per hour. So we need to convert that to meters per second, because the answer that we want, or the solution that is required, is the units should be in rev per second, and per seconds can only be found in meters per second, not in kilometers per hour. So let's just consult the not the periodic table. What is this? We're gonna consult the thingy, a formula sheet. All right, so we have two formulas that we can consider. This is the first one, circumferential velocity, where we make use of the diameter, or the circumferential velocity where we make use of the radius. But anyway, I don't think we can use, or do we have? I don't know. In fact, we have options for both formulas. Let me just do this. We have the option of using both, but I'm gonna use the one where we make use of a diameter. I'm gonna paste this here. We're gonna be using this formula in this discussion. So velocity is equals to pi diameter n, where the n is the number of revolutions. Okay, so like I said, the velocity is given to us in 60 kilometers per hour. So we need to convert this velocity into okay, is it? Oh yeah, okay. Therefore, we'll have to convert the kilometers per hour to meters per second. So I'm just gonna divide by 3.6. So 60 divided by 3.6 gives us a 16.67 as meters per second. Right, then I go back to the formula. I substitute the velocity, that is 16.67 equals to pi diameter. We did calculate, it's that one, it's 1.37, and then this is n. Therefore n is going to be equals to I just hope that you know how to manipulate formulas, but this one is straightforward. We're just going to divide by the pi and the 1.37. We're going to end up with a 16.67 divided by pi 1.37. So the answer is going to be 16.67 divided by pi 1.37. So the answer is 3.87 revolutions per second. So this is the answer. Had we continued with the kilometer per hour, the answer was going to come out as revolutions per hour, provided that the diameter we are substituting is also in kilometers. So whenever you do substitutions or do calculations, just make sure that the units match. You are working with meters, there should be meters everywhere. You are working with seconds, there should be seconds everywhere. Okay, so that's 10.1.3. 10.2, the second part of the question. The picture and the diagram below show the area covered by a light beam cast by a torch lying on the floor. The light beam covers a distance of, and the beam angle it's pi, not pi, what is this, alpha. The area covered by the beam of light is this. Okay, so the area that is covered by that light beam, it's this shaded area, this part, it's the area the question is referring to. It's this area right here. So that the length of the size of that area, it's what? It's 2.5. It's 2.5 meters squared. Right? So show that alpha in degrees is an acute angle. Justify your answer. One thing for sure, in fact you should know this, that an acute angle, let me just say, an acute angle is an angle that is less than 90 degrees. That's an acute angle. So we need to just do a calculation, work out alpha. If alpha comes out as an angle that is less than 90 degrees, then we just proved that the angle is an acute angle. So consulting the formula sheet again, area of a sector, that is in fact a sector, that is a sector. So area of a sector is this. I'm not gonna copy that. I just hope I remember the formula. So the area of a sector is equals to what does it say? R squared, and then theta, that is the angle, divided by 2. So we do have the area of the sector, it's what? 2.5 equals to, what is the radius? The radius, it's this length from here, from center to circumference. That's the radius, 1,8 squared. Then we have alpha is theta. Divide this by 2, divide by 1, cross multiply. We get a 2.5 multiplied by 2, a 1.8 squared pi divided by a 1.8 squared, a 1.8 squared. They cancel, then alpha is equals to 2.5 times 2 divided by 1,8 squared, and then we get a 1.5, a 1.54, 5.43209.877. So the answer we get, it's in radians. So this formula assumes a measurement of radians. So whenever you do the calculation, you need to substitute radians. Area of sector, oh, there we go. So this formula, the radius represented by RA is a central angle in radians. So you always do or substitute radians when working with that formula. So the answer we got, it's in radians, right? It's in radians. Now they want us to show alpha in degrees in brackets, right? So we need to convert this into degrees. How do we do that? We say that angle 54320.9877 times 180 divided by pi. So we say 180 over pi, and I'm getting an 88.42. 88.42 degrees. Therefore, the 88.42 is in fact less than 90 degrees. So therefore it is acute. Therefore it is acute. It is acute. Okay, I just need to erase this part now. This should go away so that I can answer the 10.3. This is somewhat a question related to Euclid. So it's 10.3. The picture and the diagram below show the circular top of a can with center O. Okay, let's use this. That's the center, that is the center. This is the picture, this is the diagram. Okay, so with center O, the radius OB is 26. This is 26, that's OB. AB is a chord and the height. Wait. AB is a chord and the height MC of the, okay, no, I see. So as demonstrated, we have a chord AB and the height of the smaller segment, that's 20 millimeters. Perhaps let me do this. This represents the radius. This as well represents what? The radius. A length that is measured from center to circumference is the radius. Now the question says calculate the length of chord AB. So what we are looking for is the green. Okay. We are looking for this green part. I like highlighting because I can. Because the software allows. No, I'm joking. It makes the conversation to flow much more easier. Okay, so we are looking for AB. So, okay. All right. Okay. The radius, okay. Some information is missing here. Something is missing. Maybe they forgot to say this should be equals to that. I think that's what they forgot to mention here. But anyway, if I connect O and M like this, I should have a 90 degrees right here. Okay, I should have a 90 degrees right there. Now, I have OB as 26. It also means that OC is also 26 because they are both radii. OC is equals to OB. They are both equals to 26 millimeters. It's because of they are radii, like this. Therefore OM is equals to the 26 minus 20, that is equals to 6 millimeters. So we have a small 6 millimeters right here, and then we have OM, then we have we have OM as 26. Then we are looking for MB so that we can calculate the AB as a whole, like that. Okay, so like I said, I sort of feel like they forgot to mention to us that this is equals to that, so that we can draw a conclusion that that angle OMB is equals to 90 degrees, so that we can apply Pythagoras theorem. Without that 90 degrees, we cannot apply Pythagoras. But for this problem, I'm going to take it as a 90 degrees. Okay, so Pythagoras says what? It says hypotenuse squared, which is that OB, is equals to side OM squared plus MB squared. Then we substitute OB, it's 26, OM, that's 6, plus MB, I don't know. So 26 squared is equals to 676, 36 MB squared. Then you have a 676 minus 36 is equals to MB squared. 676 minus 36 is equals to 640 is equals to MB squared. Therefore we take the square root, we take the square root as well. 640 is equals to 8 square root 10 is equals to MB. Therefore the MB rounded off to 2 decimal places, that's going to be a 25 comma 30 millimeters. Therefore AB should be equals to 2 multiplied by the MB, because this is equals to that. So by multiplying the 2, by multiplying MB by 2, we can get MB, right? So 2 times 25,30. 2 times 25,30. So the answer is what? It's 50,6 millimeters, like this. Like this. Are there any questions? Now we jump to the last question of the question paper. So for this last question, we have the mid-ordinal rule, where we find the area of an irregular shape, 11.1. For the 11.2, we have a question on measurement. Okay, so the picture of an irregular figure with side AB is shown below. We have the ordinates of the figure, which are basically the heights. They are varying in length: 2.96, 6.99, 3.98, a 2 is 6.05, and a 3.99. A right angled triangle ABC with AC being equals to that, BC being equals to that, is not part of the irregular shape, but it's outside. Let me just highlight the triangle like this. This is the triangle that is not part of that irregular shape, and it's a right angle triangle. Calculate the length of AB to the nearest integer. So that is 11.11. 11.11. So we want AB. So since that is a right angle triangle and it happens to be the hypotenuse of the triangle, the AB that we want to calculate, so we can use Pythagoras theorem. We're going to say AB squared is equals to AC squared plus BC squared, like this. And then AC, it's that 11.18 squared, BC, that's 10 squared, 11.18 squared plus 10 squared equals to, we get 224 24 centimeter squared. Therefore AB is gonna be equals to 15 when rounded off to the nearest integer, so that is 15, because it's 14.99997. 4666. Okay, so when you round it off to two decimal places, anyway, it's gonna give you a 15. So yeah, AB 11.1.2. If AB is divided into 5 equal parts as shown in the diagram, determine the width of each of the equal parts. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, it's divided into 5 parts. So we take AB and divide it by 5. We're gonna divide it by 5. So that's gonna be equals to 15 divided by 5 is equals to 3 centimeters. 3 centimeters. So what are we looking for now? In the next question we have 11.13. 11.13. What do they want us to calculate? Hence, determine using the mid-ordinal rule the area of the irregular shape. So now we want the area of this shape in particular. Let's use green. Let's use green. We are looking for the area of this shape, of this irregular shape, this green shape, using or applying the mid-ordinal rule. The area is equals to A, open bracket. Actually, I'm not sure if I remember the formula off by heart, but it's this formula where we use the mid-order. Or we can use that one, but let's just stick to this one. It's much more quicker. It's much more quicker. I'll have to copy. Let's copy and bring it over here. This is the formula. So total area, the A represents what? Let's go back. Where A, it's the width of each equal parts. Is the width of each equal part. So that width, it's actually the one we calculated above, where we divided AB by 5 equal parts. So area is equals to A in bracket O1. O1, it's gonna be this. This is O1. This is gonna be ON, the last ordinal. What is this? Last ordinate, right? So the first ordinate is 2,96 plus the last ordinate, that is 3,99, divided by 2 plus the rest of the ordinates. How many do we have left? 4. So it's 6,99 plus 3,98 plus 2 plus 6,05 plus 3,99. I'm joking. So we started with this, which went into that. The 399 substituted here, and then the rest of the ordinates, they go straight to the 02, 03, 04, and then we have that. Alright, so I'm just gonna punch this in on the calculator. 3 open bracket, we have a 296 plus 3,99, 2 plus 6,99 plus 3,98 plus 2 plus 6,05, close bracket. I'm getting a 67,49 units centimeter squared. Okay, that was a fun question. Next and the last question of this question paper. The diagram below represents a cylindrical design of a storage container. with identical cones on both ends. So we have a cone similar to that cone at the bottom, like that. Right. The diameter of the cylindrical part is 3.67 meters, and the total height is 9. Oh, I see. It's 9.65. So the height, just be careful, be careful. The height starts here. It measures all the way to the tip at the bottom, that one. The height of each cone is 1.5, so it also means that the height of the cone at the bottom is also 1.5. If I were to say maybe 9.56, subtract the 1.5 and subtract another 1.5, I'm getting a 6.56, which is the length from here all the way to there. Okay, all the way to the bottom right there. Okay, so not that it's needed, but I'm just putting it out there so that we can, maybe it's gonna come in handy. Okay, yeah, look at B. The slant height of each cone is that. So the height, it is a height, but a slanted one. So it measures the sides of the height on the sides of the cone. Okay, so we are given the volume of a cone formula, volume of a cylinder formula, and a volume of a cone, total surface area for the cylinder, total surface area for the cone, where L is the slanted height of the cone. Here, 11.2.1 A, the length of the radius of the cone. So since we are given a diameter which is equals to 3.67 meters, the radius is going to be calculated like this. Take the diameter divided by 2. Divided by 2. Determine the length of the radius of the cone in meters. Yeah. So that's gonna be 3.67 divided by 2. I'm getting a 1.84 meters. Yeah, it's in meters. And then B, the height of the cylinder, I think we worked this one out. It's that 9.56 minus 1.5, which is this height from here to here, minus another 1.5, which is the height from here all the way to there. The answer is 6.56 meters. That's the height of the cylinder. Then we have at 11.2.2. Calculate the volume of the container. Okay. By volume of the container, what do they really mean? Is it the volume for the entire container or just a part? No. Okay. You know what? I'm just gonna calculate the entire the volume for the entire shape. So I'm gonna calculate the volume of the cone at the bottom, at the top, as well as the cone at the bottom. Since they are identical, I'm just going to calculate the volume for only one cone and multiply it by 2. So volume of cones is equals to 2 multiplied by volume of a cone. It's this one. It's 1/3 multiplied by pi multiplied by the radius. It's that one. Yeah, it's that one. It's 1.84 squared multiplied by the height of 1.5. Is it 1.5? Yeah. Then it's 2 times. Now remember, I was using or applying this formula. Volume of cone, it's this one, and I have to multiply by 2 because there's 1 2. They are identical. Just a quick reminder there. Multiplied by shift pi multiplied by 1,84 squared multiplied by 1,5. The answer is 10,64. Yeah, 64 meters cubed. 1, 2. Now we're going to calculate the volume. We're now going to calculate the volume of the cylinder. The middle part now. It's time to calculate volume of the middle part, which is a cylinder. So a cylinder volume, it's this one. And it's only one. So volume of cylinder is equals to okay, it's pi r squared times h, pi multiplied by r radius, it's that 1,84 squared multiplied by the height. Height is what? Is 1,5. Shift pi multiplied by 1,84 squared multiplied by 1,5. Then we have a 15,95 meters cubed. Therefore, V total, it's 10,64 plus 15,95. 15,95 plus 10,64. 10,64. Wait. Okay, wait. Alright, I got that. Okay. No, something is wrong. I knew the volume cannot be that small. I was getting like something like 25-ish, something like that. It's supposed to be higher, man. It cannot be that. It's okay. The error was actually with the height. The height was supposed to be that 6.56, the 6.56 like this. So this is not the answer. Pi 1,84 squared times 5,6,56. Answer 69. A bit higher, but yeah, it kind of makes sense. And then meters cubed, and then we're gonna add the above, the one above I don't have a problem with. 6977 10,64 plus 69,77. Then the answer is 80 80,41 meters cubed, like this. So that's the total volume. And then for the final answer, 11.2.3, determine whether 100 cubic meters of the material is sufficient to cover the container. Now we want the surface area. We want to calculate the surface area now. So let me try to squeeze in the calculation in this smaller area. Alright, so let's use maybe red for this one. So that's gonna be 11,2,3. So there's two cones. So surface area of cones is equals to 2 times surface area of a cone. It's that one. So it's gonna be open bracket pi r squared plus pi r slant height is equals to 2 times, what is pi? Pi is pi multiplied by radius Radius, it's the radius of that cone. It's 1,84 squared plus pi times 1,84 no squared multiplied by the slant height, which is 2,37. It's given 37. Alright, let me make sure that I punch this one correctly now. Times 1,84 squared plus pi 1,84 times 2,37, and then the final answer is okay, the final answer is gonna be 48. Let's check 48 comma 67 cubic, square centimeters. I'm still thinking about the cylinder now. The cylinder is on my head now. I'm thinking about it quite a lot. Okay, but anyway, it's 2 pi r. Okay, 2 pi r squared plus 2 pi r h. Now this is equals to 2 times pi times r, which is that radius, the radius of the cone, 1,84 squared plus 2 pi multiplied by 1,84 multiplied by the height, which is 6,56, not 65, 6,56, yes. And then the answer, it's 2 times pi times 1,84 squared plus 2 times pi multiplied by 1,84 times 6,56. Okay, that's 97,11 centimeters squared. And then the surface area, the total surface area is going to be equals to 48,67 plus 97,11. 48,67 plus 97,11. So the answer is going to be 1, is equals to 145,78 square centimeters. Now the question is, will the material be enough? No, so we're going to be covering a 145,78 area. So 100 square meters will not be enough. Oh, okay. Hang on. Wait a minute. Okay, the lengths are in meters. Okay. Okay, wait. Something is happening here. You know what? Whoa. Okay. Ish. You know, measurement can mess you up sometimes. Look, the whole calculation is not completely wrong, just I made a couple of assumptions here. Look, the total surface area of a cylinder, it's gonna be this. In fact, let's do this. Let me say surface area of cylinder is equals to 2 pi r squared plus 2 pi rh. Okay, so the surface area of the cylinder doesn't include this part. It doesn't include this part. A cylindrical shape, it's like this. It's like this. It's like this. Okay. So let me just maybe put back the 2 pi r squared plus. This 2 pi r squared actually represents the top part and the areas of the bottom part, right? Going back to this shape, this bottom part and the top part of the cylinder are not outside, they are inside the shape. So inside the top and the bottom part of the cylinder, they're not going to be covered by this material, so we're going to disregard this part of the formula. Okay, we're going to disregard this part of the formula. Then we're going to have another discussion on the surface area of the cone. So the cone, no, that's the volume. The surface area of the cone as well, the same thing applies. This pi r squared, this is your cylinder, not your cylinder, your cone. This is your cone. This part of the cone is represented by the pi r squared. Represented by the pi r squared. So we're going to disregard this part of the formula because it's not exposed. The material that is going to be used to manufacture that container, it's not going to cover for the bottom part of the cylinder. So we disregard that part of the formula. This pi r squared plus pi rl it's going to be disregarded. So we take this out. We're only going to add 1 and 2. 1 and 2. But the cone, I need to multiply that by 2. Why? Because we have one cone at the bottom and another one at the top. Therefore, the total surface area is equals to, yeah, what a question. It's easy to assume or to be sidelined and getting it wrong with this one. So just be careful, just be careful, just be careful. I knew I was off a little. I had to revisit my calculation. So the radius, there's only one radius. The radius is that 1,84, and then the height, by height we mean height of the cylinder, that's 6.56 plus 2 pi multiplied by the radius. The radius, there's only one radius, the 1,84, and then we have the slanted height, 2,37 equals to 2 shift pi multiplied by 1,84, 6.56 plus 2 pi multiplied by 1,84 times 2,37, and then I get an answer of 103.24. So the conclusion is no, not sufficient. Not sufficient. Yeah, what a question, what a question. Luckily I picked that up quickly, or after finishing the calculation, because yeah, you guys, you're gonna chow me in the comment section, be like, you say got it wrong, he doesn't know what he's doing. Hey, this guy. All right guys, thanks for tuning in. Check the description box of this recording. You're gonna see links for the complete recording of this video if you are watching a segment of this entire video. Yeah, if you enjoyed, leave a like. You got a question, let's talk in the comment section. There's also I also offer one-on-one tutoring sessions. If you want a one-on-one kind of session, just I'm gonna leave all the details of the tutoring services in the description box. If you need that service, let's talk via WhatsApp. I'm gonna leave my number. If you wanna be more professional, I'm gonna leave my email address as well. And then yeah, thanks for tuning in. Don't forget to like, share, and subscribe. I appreciate y'all. Catch you on the next recording.